And welcome again. We have one more problem. This problem is a standard. This is an example of forced oscillation. Why? You read the statement of the problem, you will understand why. The statement of the problem is a ball of mass m is suspended on a spring of a spring constant k. Call it a spring pendulum. I have no problem. The suspension point of the spring performs vertical harmonic oscillations with amplitude A and frequency omega. If the ball was simply suspended on a spring, it would have oscillated itself. But now its point of suspension is also oscillating. That is why it's a forced oscillation. And the amplitude of forced oscillation is A and the angular frequency is omega. Find the natural frequency of oscillation, that is oscillation of the ball, and equation of motion of the ball during undamped oscillations. That means you are free to use the mechanical energy conservation. First of all, let me tell you the natural frequency of oscillation is under root k by m and nothing else. We'll call this omega naught because omega is something else frequency. And I have drawn a picture of this oscillation at any time t, and you can see it. And I have shown that at any time t, this point of suspension has moved the distance a sine omega t. Its amplitude and omega all was given, and it was initially at its equilibrium position. So at any time t, its displacement can be simply written as a sine omega t. And this is the equilibrium position of natural frequency of this load, this ball mass m. And this is L naught. L naught is the natural length of the spring, so that this is L naught plus mg by k, that is the extension produced by putting the mass m with the spring. And so that this natural length of the spring after putting the ball of mass m to it, its length has been increased by L naught plus mg by k. This is the length of a string in this direction from the point of suspension, and this is the extension of the spring. And that means you have to find out x as a function of time in this problem. So this is a little bit extra that you gave it to from the equilibrium position. The ball has been displaced by length x and it's downward. No problem writing this. So let us write down the Newton's second law of motion for the ball, and we know an mg will be acting downward. That means we have taken positive direction of x-axis in downward direction, and this whole thing is x-axis. And the mg minus the spring will exert a force according to which it has been extended from its natural length. So this length I would like to write it simply delta x, and that will be equal to m d2x upon dt square, mass into acceleration. And what is this value of delta x here? Delta x is total extension in the spring produced, and that will start from mg by k plus x plus a sine omega t. This is also the extension in the spring. This is the full extension of the spring. And After putting the value of delta x, we are going to get something mg minus k mg by k minus kx minus ka sine omega t, that is equal to m d2x upon dt square. And after these things gets cancelled out, I can write the equation as m d2x upon dt square plus kx equals minus ka sine omega t. This is okay. So we need to solve this differential equation, and I know the solution of this differential equation can be of the form, that means we need to find x in terms of t, and that will be in this form: x equals a sine omega t plus b cos omega t, and where a and b are some constant coefficients that need to be determined. And how? So we are going to take the derivative twice, and we can substitute it into this equation 1, and we will obtain the values of a and b. So I'm going to get this. So on this, and dx by dt will be simply a omega cos omega t minus b omega sine omega t. Okay, fine. And d2x upon dt square, this is the main thing to get here. This will be minus a omega square sine omega t, and this will be again minus b omega square cos omega t, cos omega t. And we have to put all those values, this value of x and this value of d2x upon dt square into this equation. We are dealing with a forced oscillation, so we will not need dx by dt, of course, I know. So this is all right, and I'm going to write down the equation. So it becomes m minus a omega square sine omega t minus b omega square cos omega t, and plus k a sine omega t plus b cos omega t, and that will be equal to minus ka sine omega t. That's right. And this is the equation. And trick to solve this equation, that this equality must be satisfied for any moment of time. For all values of time, this equality must be satisfied for all values of time. So I am going to take some convenient values for the solution. Let us put t equals 0 and t equals pi by 2, because we need to find out two unknowns. So we will be needing two equations, and we can do this. First, I would like to do something. I would like to take sine omega t and cos omega t common in this equation, so that I can write here sine omega t minus a omega square m plus ka, and plus cos omega t, it will be minus b omega square a m plus kb, and it is equal to minus ka sine omega t. Okay, right. And I would like to put first the value the value of t equal to 0. This is the trick to solve this problem. You can take any value of t, you wish, because this is valid for all values of t. Otherwise, it doesn't mean anything. So I'm going to put t equals 0, and I can get sine omega t equals 0. That means whole thing is 0, and cos omega t equal to 1. And this thing is also 0. That means I'm going to get minus b omega square m plus kb equal to 0. And if I take b as common, that we will get k minus omega square m equals 0. This is valid for either b equals 0 or k minus omega square m equal to 0 or both 0. So I'm not sure yet now, so I'm going to keep it in this way. And now I'm going to put the values of t equals pi by 2 omega. T equals pi by 2 omega. Yeah. That means I'm going to put omega t equals pi by 2. The value of t I will select now as t equals pi by 2 omega. So that sine omega t will become sine pi by 2 or cos omega t will become cos pi by 2. And this value is 1 and this value is 0 and this value is 1. That means we can get something like here minus a omega square m plus ka, and this value is 0 equal to minus ka, and we take k for k as common and we will get k minus omega square m equal to minus k. That means a equals ka divided by omega square m minus k. And you can see that in this case this cannot be 0. K cannot be equal to omega square m, because in this case the denominator of a will become 0 and that is not acceptable. So this thing is not 0. That means b is 0 is the solution. And the second solution is it comes from here, that omega square m minus k is not equal to 0. Then a can be written as a divided by omega square k by m minus 1. K by m is under root k by m is omega naught. So I can write this capital A equals small a divided by omega square by omega naught square. That is the natural frequency we needed to find, minus 1. And b equals 0 is the next solution, and we can put all these values of a and b here, a and b here. In this equation b is equal to 0, so a can be put multiplied by sine omega t. So this is the equation, required equation of motion, equal to kx equals a. A is a by omega square by omega naught square minus 1 multiplied by sine omega t, and this is the equation of motion of the ball. Yeah, and I solved it. Thank you very much for watching.